Hello and welcome again. In this video I'm going to talk about the conservation of energy concept, and then in the next following videos I'll talk about how to use the concepts to solve problems. So previously in physics we learned that there's a relationship between work and energy, how work can actually describe another way of modeling systems using the concept of energy. And like I said before, some of the benefits of using energy is that it's a scalar property in which we can just identify three things. Either it's a velocity for kinetic energy, a height for potential energy, or a stretch for elastic energy, and use those triggers or those keywords to help us identify initial and final conditions to figure out some information in our systems. So I know that was super vague, but I'll go through several examples to explain how that might work. So first I got to describe what is called the difference between conservative and non-conservative forces, because that's going to address some conditions in terms of how we apply conservation of energy. And then I'll model many different types of problems to solve with it. So first is the difference between conservative and non-conservative forces. Conservative forces are path independent, which means it doesn't matter what the object does, all you care about is the initial and final condition. So for example, if I take this ball right here and I lift it up 3 meters, it's going to have the same gravitational potential energy if I took the same ball and moved it up a ramp to the same height. Now, if you recall gravitational potential energy as an example, let me just get my pen out. Give me one quick second here. Or actually, you know what? Change my mind, sorry. Let me get this pen. Oops, and go back here. Okay, so GPE, MGAs for an example, we just care about height. So it doesn't matter how the ball got there. Let me fix that. It doesn't matter how the ball got there because the height is the same for all three of these. These are path independent. So I could have pushed this ball up the incline and ended here, but my height is still 3 meters. And in this example, I could take the ball and make it go upstairs, and as long as it ended here at 3 meters, these all have the same gravitational potential energy, which means it has the same amount of gravitational potential energy. Because of this, we call it a conservative force. So conservative forces also include electric potential energy, so stretching. So we don't care about its motion, we just care about its initial and final measure of this. This should be M, sorry, M for mass. We just care about this stretch. So elastic potential energy kind of works on the same principles, and eventually when we get there, electrical forces. So these are our conservative forces. Things that are not conservative, so those are things that are path dependent, which means that the force changes with distance. So what do you mean by that, right? So first of all, our biggest one is friction right here, because if you look at my little example right here, I could take a book and I could follow the red path from here to here, or I could follow this blue path. Now I hope you notice that the red path is longer, which means that friction will take away more energy because it has a longer time in contact with the table, and therefore it will have more energy loss due to that, versus the blue path right here will have less distance covered, which means friction will act for a lower period of time. So when you have a force, and you have a force where distance actually matters, that's a non-conservative force. So the biggest one, like I said, is friction. That's the one that's going to really going to matter. Force applied. So as you might imagine, the longer you push the force, the more that object changes its motion. So these are non-conservative forces. Tension is technically considered one, although we're really not going to study that. And force drag or air resistance. As you might imagine, the longer the object's falling, the more air resistance that object will feel. So these are all non-conservative forces. So we need more forces. You know, the more distance you have, the more that the force acts, which means you have more work done. So this is like added energy to your system. So, why do we care about conservative and non-conservative forces? Well, it has to do with the law of conservation of energy. So an isolated system, so what I mean by isolated, so we're assuming nothing else is interacting, so mostly we're excluding friction here. So, a non-conservative force, we're looking at modeling only conservative forces. Then we get conservation of energy, which means that the energy of the system will remain constant. So you might have heard of the phrase that it can never be created or destroyed, just transferred. Basically, it just means that the system's energy will remain constant so long as you don't do any outside work. As soon as you do outside work, then yes, your energy of the system will change. So we can write this in a couple different ways. So mechanical energy refers to the three energies introduced earlier, so kinetic, potential, both gravitational potential and electric potential. Of course, this is definitely different than thermal energy, different than chemical energy, different than electrical energy, because it's based on position and velocity, so that's why it's mechanical energy. So, although I have it written here, I don't really like these forms. We're going to go to here. So long as we have non-conservative forces on our system, then the total mechanical energy is conserved. That's what this means. This means total, I just rewrote the words, which is really silly. Just total mechanical energy. There you go. That's better. And, of course, total means to sum these up. So, basically, the change of the total mechanical energy of the system will have to be and remain zero for energy conservation. So the total energy initial minus the total energy final minus the initial will be zero. But I like writing it in this form right here, because if I write it in that form, then I can organize my systems into the initial conditions and the final conditions, like this. And in fact, I can kind of expand this out into something more like this. So, KE initial plus PE initial equals KE final plus PE final, like that, right? So remember, KE is 1/2 mvi squared. Now the I represents initial and potential initial. And then I'm just expanding this out, I hope you notice. Like this. So my favorite example is something like this. So it could be like a skier. It doesn't have to be, but I could have a skier. There you go. Beautiful. At some height h, with some initial velocity v, and this could be my initial condition, and my final condition can be at any point. I'm going to choose this as an arbitrary example, where this would have some sort of final velocity and some sort of final height here, of some value here, but it doesn't matter if I can use this to solve our systems like this. Now, right now, I just model potential energy for a gravitational potential energy, but please note that this can be both or either gravitational potential energy. Oops. Sorry. I'll do it over here. Remember, PE could be both gravitational potential energy and elastic. It just depends on, you know, the system that we're modeling here. So I like this equation best when I'm solving conservation of energy. So let me go back to my slide. Give me one quick second here. So here's just a couple visuals of conservation of energy. So it means that the total energy at any point has to be constant. So I hope you notice that if we add up the total energy here, it's 50,000 joules. The total energy here is 50,000 joules. Total energy here is 50,000 joules. total energy here is 50,000 joules. Hope this is boring, because if it is, then you understand it. These are all the same value because the total energy of the system must remain constant at any point during this. So this is a skier on the mountain. And I hope you notice that these values correlate to the type of energy, right? So at the very top of the mountain, if you're at rest, you're not going to have any kinetic energy, but you'll have all potential. But as soon as you start going down the mountain right here, you'll find that you'll have a little bit of height. So you have potential, but you also have gained a little bit of velocity. So some of that potential goes into the kinetic right there. And vice versa, it correlates to each of the parts. Notice down here, you have less potential because you have less height, but now you're going faster, so you have more kinetic energy, and so forth. So here is the visual of the conservation of energy right here. You can see that the total mechanical energy bar remains constant. And then it kind of does a balancing act. So as soon as you gain height, you get more potential. And as soon as you get less height, you get more kinetic here. And you can see how they basically, if you were to add them up at any point, they would equal one another. Now notice this is for non-conservative forces. So in other words, we're not considering friction. So a pure transfer of potential goes into kinetic right here. So if you take a look at this really quickly, I'll let the animation run. So if you notice here, the skier at the initial point had both kinetic and potential energy. And then once it transferred down, it can use the combination of the two energies to go higher than it did when it was originally started. Now, if we started at rest, then this would, by law of conservation, only get up to the height that it started at. But if we're already moving, we can go higher. This, of course, is according to conservation of energy. So, now, in these slides, I know sometimes on the AP, they use U for potential and K for kinetic. So just know that this is, in fact, a potential energy. But you can analyze the energy of a spring very similarly. When the spring is compressed right here, you can have all potential energy because you have a compression. But at this point, your velocity, when you compress at the maximum point, is 0, so you'll have no kinetic energy right there. But once the spring becomes unstretched, you'll have no more potential. But as it crosses what we call the equilibrium line, this 0 point where the spring is not stretched, you're going to have all kinetic. So all of the energy and the potential goes into the kinetic. But then as you pass through and you start expanding that spring again, you're going to transfer that motion into potential energy. So now you take this spring and it moves all the way over here, and then you transfer it back to the potential case. This is identical to a skier on a frictionless mountain going up and down because it's a non-conservative force, energy of the spring. So all the energy goes into kinetic, assuming no friction. Of course, we can change things with friction, but for now, no friction. And this is just identical. These are just very similar ways to describe our system right here. And then what we can do is say that the total energy potential max has to equal the max kinetic energy. Now, I'm just going to kind of touch on this now and really emphasize that later, but you can use this as a tactic for solving problems. And then, strangely enough, this also models the same thing. When you have a little height difference, h, right here, well, we're going to have potential energy right here, because at the top, the ball, the pendulum, will actually stop momentarily. But as it swings through the bottom right here, it's going to have velocity, which means it's going to have kinetic. But if we treat this line as a 0 mark, then it's going to have no potential at that point. So it's going to have a potential of 0 and a V max, which means we're going to have maximum kinetic here. And vice versa. This goes back and forth. So pendulum is another great example of conserving energy in our system for a non-conservative force system. I'm sorry, replace that. I mean a conservative force. There's no non-conservative. There's no friction or air resistance here. And same thing, I'll model this later, but we can jump to the conclusion that all of the energy that it has at its maximum point will go into driving its potential energy at its max point too. This is combining all three because why not, right? Because we can take kinetic energy, gravitational, potential energy, and spring energy here. And the biggest idea is that you can actually use all three types of energies, elastic, gravitational, and kinetic, and we still have a conservation of energy. Okay, so in the next couple of videos, I'll stop here. I'm going to now use and apply the concepts of conservation energy to many different types of problems, so you can see how we can use it. And we'll start off with conservative forces for the first couple examples, and then the last part of my video series, you'll see that I'll do non-conservative forces, which basically involves friction for the most part. So that will end this video.